All right, so we're going to talk about several psycholinguistic experimental tasks, and we're going to start with a lexical decision task. So in a lexical decision task, the stimuli are words written on a screen. And this is visual, so they're written words, and the task is for the participants to decide whether the word is a real word or not. And what we measure, there's actually two things we can measure. We can measure listeners' accuracy, and we can measure listeners' response time or reaction time or response latency. Those all mean the same thing, abbreviated as RT. So to give you an example, this is what a participant might see. They would see the word fish and they would be asked to decide if it's a real word or a non-word. Yeah, it's a real word. Then they'd see the word flarsk and they'd be asked to decide, they'd be asked to say it's a non-word. They'd see the word hoist, that's a real word as well. Okay, so after they do the whole study, then we look at their results, and one thing we can measure is their accuracy. So if they were actually right in saying that the things that were words are words and the words that are non-words are not words. Another thing we can measure is their response time. So how long does it take them to respond? And the assumption that's pretty well supported is that longer reaction times reflect more difficult or more complex processing, whereas shorter reaction times reflect easier access or faster processing. So what have psycholinguists found from lexical decision tasks? Well, one finding has been that listeners respond faster to more frequent words. In other words, if we have a frequent English word like fish, the reaction time tends to be faster than the reaction time for a less frequent word like hoist. And what can we conclude from that? Well, it shows that the lexicon is somehow organized in a way that more frequent words are easier to access for some reason. And then people can argue about what that reason is, but the empirical finding is that more frequent words are more quickly responded to. Another finding is that listeners respond faster to non-words that are phonotactically legal. In other words, people are faster at saying blick is a non-word than bnick. Phonotactically legal, that means that it's a legal word of the language, even though it's not a real word. And what this shows is that somehow phonological knowledge must play a role in lexical access. Okay, next, priming. So, priming task. Again, in a priming task, we're looking at written words on a screen. And in this task, what the participant will see is first they'll see a word that's called a prime, and then they'll see a word that's called the target word. And their task is to do a lexical decision task, which we just talked about, on the target word. And this time we're usually interested in listeners' response time. So I'll show you how it works. So remember, first you're going to see a prime very quickly and then a target word. So an experimental trial would look something like this. Okay, so did you see that? So first of all, you very quickly saw the word doctor, and then you saw the word lion, and now you're asked, so doctor was the prime, lion is the target word, and you're asked to decide if lion is a real word or a non-word. And that's not, okay, let's do it again. So, and now you saw doctor and then elephant, and you decide if it's a real word or not a real word. Okay, so why would we possibly want to do this? Okay, well, here's the deal. There's this thing called a priming effect. And so for that prime, notice the participant doesn't have to do anything at all. They could just ignore it if they wanted, right? That very first word, because all they're doing is just saying whether the second word is a real word or not. But the interesting thing is that the nature of that first word they see has an influence on people's response time. So for example, people are quicker to respond that lion is a real word if they've seen tiger as the prime than they are if they saw doctor as a prime. So 200 millisecond reaction time, let's say, for lion when you've seen tiger before, but a 300 millisecond reaction time when you've just seen doctor. Why would this be the case? And we can quantify what's called a priming effect by subtracting the amount of time it takes for the longer one than the shorter one. So we can say that there's a 100 millisecond priming effect in this example. And it turns out that there's a faster response to a target word if the prime is related to the target, as I just said. And interestingly, what we mean by related, well, there can be a lot of different relationships. So for instance, the example I just showed you was what's called a semantic prime. So you're more quick to respond that lion is a real word if you've seen tiger, which is semantically related, than if you've seen doctor. However, priming also helps speed up responses to words if the words have phonology in common. In other words, you're quicker to respond to bite if you've just seen light than if you've just seen crib, because bite and light are phonologically related, they share a rhyme, whereas bite and crib don't have much in common. You can also have orthographic primes where if you see something that's spelled more similar, so couch and touch, even though they're not phonologically related or semantically related, you're going to be quicker at responding to touch than if you had an unrelated word like close. So all of these different types of relationships can speed up reaction times. Okay, the last two types of tasks I'm going to talk about are identification and discrimination. And in order to talk about these, I want to introduce the idea of a phonetic continuum. Now, we've talked about aspiration before, and remember in English, word initially, well, actually stressed syllable initially, or at the beginning of a word, voiceless stops are aspirated, whereas voiced stops aren't. So I'm going to play you a continuum going from short aspiration to long aspiration, systematically. In other words, all of the steps are equidistant. Ba, 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 ba. I'm going to play this for you again, and I want you to think about what you hear for each of these. Ba, 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 ba. Okay, so hopefully you're hearing ba and pa for all of them. And an identification task is a task where basically you just play people sounds or you show people words or something and you ask them to identify them. So you could have a task like, do you hear pa or ba? And I would play you a bunch of sounds. Like I would just play pa, and I would say, do you hear pa or ba? Now, in this example that I just showed you this continuum, but in a real experiment, in the experiment I'm going to talk about, using this example here, you would play those different continuum steps, but not in order. So they would hear something like, first they would hear ba, 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 ba. And for each of these, so actually I'll break it down so you go like this. Pa. Did you hear pa or ba? And you decide. Ba. Did you hear pa or ba? So you go through and you do this, each trial is a different sound. Now I'm going to go ahead and jump to the discrimination task now too, because we're going to use the same stimuli. So a discrimination task, discrimination in this sense just means deciding whether things are the same or different. So can you tell the difference between them? So you'd hear something like this. Ba, ba. And I would ask, are these two sounds the same or different? And probably there you would say different. And again, we could choose different stimuli from that set I showed you before. Ba, ba. Maybe you think those are the same. Ba, ba. Maybe you think those are the same. And if you were actually in class, I would make you do this experiment right now, and then I would graph the class's results. So I'm sorry we're not able to do that. That would be a lot more fun. But anyway, the reason I'm talking about these tasks right now, I'm actually going to slip in some phonetics here. Actually, I'm going to play you all of these pairs. So I want you to think for each one whether they're the same or different. Ba, 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 ba. Okay, so for some of those pairs you might have heard differences, for some of them the same. Actually, as you may or may not have guessed, all of those were different. So I was actually playing you all different pairs of sounds. And this brings us to a sort of interesting concept. It's called categorical perception. And as listeners, we perceive usually sounds within the same phonemic category as the same. We've talked about this a little bit in L2 acquisition, right? Remember when we learned that it's harder to tell the difference between two sounds that are allophones of the same phoneme, right? So this is sort of generalizing that a little bit. It's easy to hear the difference between two sounds when they're from different phonemic categories. Or in this case, if we're thinking of a continuum going from B to P, it's easy to hear the difference between two sounds when they're across that BP boundary. But it's hard to hear the difference between the two sounds when they're in the same category. And the other interesting thing is that we don't, like usually when you listen to that continuum, at some point it just switches from B to P. It's not like you hear something as sort of B or sort of P-like. And this concept, these two things together, are called categorical perception. And if you look at this graph, so this is a graph, on the x-axis it shows 5 different tokens, and this is like our aspiration continuum, going from short to long aspiration. And so if short aspiration should sound like ba and long aspiration should sound like pa. On the y-axis, we have the percentage of the time that people are hearing ba versus pa in their identification task. And you'll notice, so like it might be, so it could in principle be possible that this would be sort of a line going down, like this one really sounds like ba and this one really sounds like pa, but in the middle they sort of sound in the middle. That's not usually what happens though. Instead, people think this one sounds definitely like ba, this one definitely sounds like ba, this one definitely sounds like ba, and then it completely switches. And these guys start sounding like pa. And so this sharp category boundary is why it's called categorical perception. That's the so that's what results of an identification task might look like. Then if we think, so this is a little bit confusing graph to put on top of each other, but what this graph is it's a graph of discrimination results. And each of these triangles represents how well people were able to discriminate between two contiguous stimuli. So how good were people at discriminating between 1 and 2? And this is at 50%. 50% is chance. So this means they can't discriminate between 1 and 2. They sound the same. This one, between 2 and 3, they also can't discriminate, sound the same. And between 4 and 5, they also can't discriminate. And this is because these are within the same category. However, when you look at the difference between tokens 3 and 4, when you ask people whether they could tell the difference, they're really good at it. And that's because it straddles a category boundary. So this is the concept of categorical perception. Now, remember the babies? Of course you remember the babies. So remember how this classic study where English infants were able to discriminate at 6 to 8 months these Hindi and Salish sound contrasts, but then by 10 to 12 months, the kids are not good anymore. They're just as bad as adults, and they can no longer discriminate them. This is because they've lost the ability to discriminate between sounds that are members of the same category in their language. So again, linguistic development is a loss of perception of unimportant sound distinctions. Okay, so to summarize, what can we see from the findings from these psycholinguistic tasks? Well, from lexical decision tasks, we've learned that word frequency and phonological knowledge are both used in language processing. From priming tasks, we've learned that the mental lexicon includes connections based on semantic, phonological, morphological, and orthographic information. Identification tasks show us that sounds within the same phonemic category are identified categorically. And in discrimination tasks, we found that it's difficult to tell the difference between sounds coming from the same phonemic category.